Good morning, students. Today's topic is application of derivative. Objectives. Some applications of derivatives are as follows. Mean value theorems. Number one is Rolle's theorem, its geometrical meaning, Lagrange's mean value theorem, its geometrical meaning, approximation of differentials, increasing and decreasing function, maximum and minimum, extreme and critical points, tangent and normals, and class exercise. Now, number one, Rolle's theorem. Let fx be a real function defined on the interval a to b such that function is continuous in the closed interval ab, function is differentiable in the open interval ab, and fa is equal to fb. Then there is a point c in the open interval such that f dash c is equal to 0. Means c lies between a and b. Its geometrical meaning is like that. This is the function where fa will be equal to fb, where fa and fb both are shown on y-axis. We have in figure 1, and fx is continuous and differentiable in both figures. Then if we join a to b directly, then AB is the line parallel to x-axis whose slope is 0. Therefore, f dash c will be 0 and c lies between a and b. There will be at least one point in the interval AB where tangent of the curve will be parallel to x-axis. Example. Verify Rolle's theorem of the function fx equal to x square minus 8x plus 12 on the interval 2 to 6. Solution. We have fx equal to x square minus 8x plus 12. Given function fx is a polynomial function. Therefore, fx is continuous on 2 to 6. And we know that its derivative is 2x minus 8, which exists in 2 to 6. Therefore, fx is differentiable in 2 to 6. Now, f2 is 0 and f6 is also 0. Therefore, f2 is equal to f6. All the conditions of Rolle's theorem is satisfied. Then there exists some c belongs to 2 to 6 such that f dash c is equal to 0. Implies that 2c minus 8 equal to 0. It means c is equal to 4. Now 4 lies between 2 and 6. Hence Rolle's theorem is verified. Example 2. Using Rolle's theorem, find the point on the curve y is equal to x, x minus 4, x belongs to 0 to 4, where the tangent is parallel to x-axis. Solution. Being a polynomial function, the given function is continuous in 0 to 4. Y dash is twice of x minus 2, which is also exist in 0 to 4. Hence, function is differentiable from 0 to 4. Now, f0 is equal to 0 and f4 is also 0. Therefore, all conditions are satisfied. Now, an element belongs to 0 to 4 where f dash x equal to 0 will be x equal to 2. Now, when x equal to 2, y is minus 4. Required point is 2 comma minus 4. Now, second is Lagrange's mean value theorem. Let fx be a function defined on AB such that fx is continuous on AB and this is also differentiable in AB. Now then there exists a real number C belongs to AB such that f dash C is equal to fb minus fa upon b minus a. Its geometrical meaning is, if a curve start from A to B, fa is not equal to fb, then if we join A to B, then slope of AB is equal to slope of tangent. Therefore, slope of AB will be fb minus fa upon b minus a. Hence, according to Lagrange's mean value theorem, f dash C will be fb minus fa upon b minus a, implies that tan phi is equal to f dash C. Slope of the chord AB is equal to slope of tangent at C minus a. Example. Verify Lagrange's mean value theorem for x cube minus 3x plus 2 on the interval minus 1 to 2. Solution. Fx is a polynomial function, therefore it is continuous in minus 1 to 2. Now f dash is 2x minus 3 which exists in minus 1 to 2, therefore fx is also differentiable in minus 1 to 2. So there exists at least one C belongs to minus 1 to 2 such that f dash C is equal to f2 minus f minus 1 upon 2 minus minus 1. Implies that 2c minus 3 is equal to 0 minus 6 upon 2 plus 1. Implies that 2c minus 3 is equal to minus 2. Therefore, c is equal to 1 by 2, which belongs to minus 1 to 2. Hence, Lagrange's mean value theorem is verified. Now, using Lagrange's mean value theorem, find the point on the curve y is equal to x cube minus 3x, where the tangent is parallel to the chord joining 1 minus 2 and 2, 1. The function being a polynomial function is continuous on 1 to y dash is equal to 3x square minus 3 exists in 1 to 2. Therefore, function is differentiable in 1 to 2. So, all x belongs to 1 to 2 such that tangent is parallel to the chord joining 1 minus 2 and 2, 1. F dash x is equal to f2 minus f1 upon 2 minus 1. 3. X square minus 1 is equal to 2 minus 2 upon 1. On simplifying, x equal to plus minus 7 upon root 3. On putting y is equal to minus plus 2 upon 3 root 7 upon 3. Therefore, required points are root 7 upon 3, minus 2 upon 3, root 7 upon 3 and minus root 7 upon 3, comma 2 upon 3, root 7 upon 3. Now, second topic is approximation of differentials. As by the definition of dy upon dx, limit delta x tends to 0, delta y upon delta x is approximate equal to dy upon dx. Hence, for a small increment in x, change in y will be delta y is equal to delta x into dy upon dx. Hence, y plus delta y is equal to y plus dy upon dx into delta x. Now, example, using differential, find the approximate value of root 37. Let y is equal to root x, where x is equal to 36 and delta x is 1, implies that x plus delta x equal to 37. Delta y is equal to root x plus delta x minus root x, implies that delta y is equal to root 37 minus 6, implies that root 37 is equal to 6 plus delta y. Delta y is equal to dy upon dx into delta x. Therefore, dy upon dx is equal to 1 upon 2 root x into 1, which will be equal to 0.08. Therefore, root 37 is 6 plus delta y. It means 6 plus 0.08, which will be equal to 6.08. Now next topic is increasing function. Graph of increasing function as shown as a curve start from A to B. Its values are continuously increasing from A to B, means fx1 is greater than fx2 as x1 is less than x2. A function is said to be strictly increasing function of x on AB if x1 is less than x2 in AB, implies that fx1 is also less than fx2 for all x1 x2 belongs to AB. Strictly increasing also referred to as monotonically increasing. Decreasing function. This is the reverse of increasing function. The graph is shown as a curve start from A to B. Now if x1 is less than x2 in AB, implies that fx1 is greater than fx2 for all x1 x2 belongs to AB. Strictly decreasing is also referred to as monotonically decreasing. A function is said to be strictly increasing function of x on AB if x1 is less than x2 in AB, implies that fx1 is less than fx2 for all x1 x2 belongs to AB. Strictly increasing also referred to as monotonically increasing. Slope of tangent at any point in AB greater than 0. As tan theta is greater than 0 for theta lies between 0 and 90 degree, implies that f dash x is equal to dy upon dx greater than 0 for all x in AB. Like this. F dash x is equal to dy upon dx greater than 0 for all x in AB. Means tangent to the curve is always makes an angle acute with positive x-axis. Now for the function fx equal to 2x cube minus 8x square plus 10x plus 5, find the intervals where fx is increasing and decreasing. Now f dash x is equal to 3 times x minus 5 x minus 1. Now on f dash x equal to 0, it means x is equal to 5 upon 3 or 1. Hence x lies between 1 and 5 upon 3, f dash is negative. For x greater than 5 upon 3, f dash is positive. For x less than 1, it is positive. Now this is shown in the graph as these are critical points Q, R, S, T and so on. When the tangent to the curve makes an angle acute with positive x-axis, then the function is increasing. If the tangent to the curve makes obtuse angle, the function is decreasing. Next topic is maximum and minimum. Let y is equal to fx be a function if fa greater than fa plus delta and fa greater than fa minus delta for all small values of delta. The point is A is called the point of maximum of the function fx. In the figure, y is equal to fx has maximum value at q and s. If fb is less than fb plus delta and fb is less than fb minus delta for a small value of delta, the point B is called point of minimum of the function fx. In the figure, y is equal to fx has minimum values at R and T. Extreme points. At this point, f dash x is equal to 0. If f dash x exists, means the curve changing to increasing to decreasing or decreasing to increasing. In this graph, now P, E and Q are extreme points. At P and Q, f dash x does not exist. Find all the points of maximum and minimum, maxima and minima, and the corresponding maximum and minimum values of the function fx equal to minus 3 upon 4x power 4 minus 8x cube minus 45 upon 2x square plus 105. We have f dash x is equal to minus 3x cube minus 24x square minus 45x. On factorizing, f dash x will be equal to minus 3x, x plus 3, x plus 5. This will be 0. Then turning points are 0, minus 3, minus 5. Now f double dash x is minus 9x square minus 48x minus 45. At x equal to 0, f double dash 0 is minus 45, which is less than 0. Therefore, fx is maximum at x equal to 0. The maximum value at x equal to 0 is f0, which will be equal to 105. Now, at x equal to minus 3, f double dash minus 3 is 18, which is greater than 0. Therefore, fx is minimum at x equal to minus 3. Minimum value at x equal to minus 3 will be at x equal to minus 5. F double dash minus 5 will be minus 30, which is again less than 0. Therefore, fx is maximum at x equal to minus 5. F minus 5 is 295 upon 4. Another example. So that the total surface area of the cuboid with a square base and given volume is minimum when it is a cube. Now, let the cuboid has a square base of edge x and height y. Then volume of cuboid is v is equal to x square y. The surface area of cuboid S will be equal to twice of x square plus xy, which means 2x square plus 4xy. On putting the value of v from the given condition, 2x square plus 4x into v upon x square. For minimum surface area, ds upon dx will be 0. On differentiating, twice of 2x minus 2v upon x square will be 0. On simplifying, x will be equal to v power 1 upon 3 is equal to 4, 1 plus 2v upon x cube. Now double derivative will be 12, which is positive. Therefore, at x equal to v raised to the power 1 upon 3, surface area is minimum. Now, on putting in given condition, which may be included, which can be reached as y is equal to x. Therefore, cuboid is a cube.